Hi, today's lesson is on graphs of functions. So far, we've seen functions as algebraic expressions. We give them inputs and we get outputs. Now we're going to learn something far more interesting. We're going to graph functions on a coordinate plane, thereby having an image of the function. And therefore, we can get the geometric properties of function. Studying these geometric properties again connects us to the algebra of functions. Therefore, the expressions and the images get linked. The geometry and the algebra gets linked. Let's look at a very basic example. Let fx equal to x minus 3. Plot the graph of fx on a coordinate plane. So I need my input values or my domain values. And I'll get my range or my output values. So suppose I take minus 2, minus 1, 0, 1, 2 as my input values. X minus 3 is the function, so I'll get minus 5, minus 4, minus 3, minus 2, and minus 1. So this provides me with my set of ordered pairs. Let me write them down. So my ordered pairs are minus 2, minus 5, minus 1, minus 4, 0, minus 3, 1, minus 2, and 2, minus 1. I can plot these ordered pairs or these points on a coordinate plane, and that would give me the graph of the function. Let's see what that looks like. The first ordered pair is minus 2, minus 5. That's a point here. The next one is minus 1, minus 4. That's here. 0, minus 3. 1. 1, minus 2. And 2, minus 1. So I have my graph of the function. It's these 5 points. I do not connect these points because nothing has been specified about the domain. The domain is just given as 5 points. So these 5 points consist of the graph of the function. Let gx equal to x square plus 2. Plot the graph of y equal to gx on a coordinate plane. Use your graph to find g minus 3. What I need to do is take some domain values and get some range values. And the function is x square plus 2. So if I go minus 2, minus 1, 0, 1, 2 as usual, I'll get 6. Minus 2 square plus 2 is 6. Minus 1 square plus 2 is 3. 0 square plus 2 is 2. 1 square plus 2 is 3. 2 square plus 2 is 6. I can quickly plot this function. This 1, this 2, 1, 2. I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Look at this. This is interesting. Minus 1, 3, and 1, 3. So both minus 1 and 1 go up to a y coordinate of 3. Minus 2 and 2 go to a y coordinate of 6. Minus 2 and 2 will go to a y coordinate of 6. And 0 goes to a y coordinate of 2. These are the 5 points on the graph. If the domain was all real numbers, then I would connect these points to get all the other points of the graph. And I'd get something that's called a parabola. A badly drawn parabola, but still a parabola. Let's see what I can do with the graph. Now that I have the graph of the function, it means I have every point on the function. Let's see, they're asking for find g minus 3. So they're saying that the x coordinate is minus 3, find g of minus 3. Well, the algebraic way of finding g minus 3 is easy. I plug in minus 3 into the equation and I'll get the answer. I'll get minus 3 square plus 2. That's 11. But here we're supposed to use the graph to find g minus 3. Let me redraw the graph. So I'm redrawing the graph. 2, 4, 6, 8, 10, 12, 14, and so on. And the graph was So at 0 it was 2, At 1 it was 3, and at minus 1 it was 3. At 2 it was 6, and at minus 2 it was 6. So the graph went something like this. This is the graph of x square plus 2. G of x is equal to x square plus 2. And they've asked for g of minus 3. So I go to minus 3 on my x-axis and I go up and I find out that the y-coordinate was 11. So g of minus 3 turns out to be 11. This is a very important step. I have my graph and I'm asked to read from the graph g of minus 3. So I know the x-coordinate is minus 3. They're asking what is the y-coordinate of the graph when the x-coordinate is minus 3. So I start at minus 3 and I head up to the graph. So that's the point with x-coordinate minus 3. And they're asking what's its y-coordinate. It turns out to be 11. Find a such that GA is equal to 6. Okay. Find a such that GA is equal to 6. So I need to find an x-coordinate. They called it a, whose y-coordinate is 6. So basically the question is find a when the y-coordinate is 6. So which are the points with y-coordinate 6? I go to 6 on the y-axis and I go to my graph. And I have 2 points whose y-coordinate is 6. I find out their corresponding x-coordinates. And that turns out to be 2 and minus 2. So a can be 2 or minus 2. These are the 2 x-coordinates whose y-coordinate is 6. That's the meaning of this question. Very important to understand the question. Find a such that g is 6 means find an x-coordinate for which the y-coordinate is 6. The graph of fx is shown below. Use the graph to find f3. So in the last 2 examples, I gave you the algebraic expression, plotted the graph, and then figured out things from the graph. But we always had our algebraic expression to fall back on. Now we don't. We just have a graph and we have to read it. Find f3. What does this mean? It means x is 3. What is y? Or in other words, the x-coordinate of a point is given. Find the y-coordinate. So let's go to 3 on the x-axis. Here I am, 3 on the x-axis. So which point on the graph has 3 as its x-coordinate? This point. This point is 3 comma something. So that blue dot is on the graph and has x-coordinate 3. What's its y-coordinate? Well, go to the y-axis. The scale is minus 6, so the y-coordinate is minus 3. So this point is 3 comma minus 3. So the answer is f of 3 is equal to minus 3. Find t such that ft equal to 21. ft equal to 21. What have they given me? They've given me the y-coordinate and I have to find the x-coordinate, which is called t in this case. So the ordered pair has been given as t comma 21 and t has to be found. So I know the y-coordinate is 21. So I go to 21 on the y-axis, that's here. And then I go to my graph. And there's only one point on the graph with y-coordinate 21, this point. And they want its x-coordinate. So I head down to the x-axis and the x-coordinate is 6. So t must be 6. Confirm it. What is f of 6? Go to 6 on the x-coordinate, go up and you reach this point whose y-coordinate is 21. So f of 6 is 21. We're right. In the graph shown below, f of k equal to 2. f of k equal to 2. Find a possible value of k. So what have they given me? They've given me the y-coordinate of a point whose x-coordinate they call k. So the point is k comma 2. We need to find k. So we need to head to the y-axis to the point 2 and then check out all points on the graph whose y-coordinate is 2. So here's 2 and I go to the graph and I find that there are many points whose y-coordinate is 2. This is 1 point. And all these points have y coordinate 2. In fact, this whole line segment has y coordinate 2. So I could give this x coordinate as the answer. This is minus 2. But minus 2 is not in the choices. I could give this x coordinate as the answer. This is 2. 2 is not in the choices either. I could give this x coordinate as the answer. This is 3. 3 is not in the choices either. But any point in this line segment has y coordinate 2. So all these x coordinates work. Anything between 2 and 3 works. Is there something between 2 and 3 in the answer? Yes, D. 2.5. So when x is 2.5, we can verify that the y coordinate is indeed 2. It's this point. So this is the point we are referring to. And the answer is k is equal to 2.5. In the graph shown below, find f5 and g4. Okay, two different functions have been plotted on the same graph, the function f and the function g. And we have to read them. No big deal. F of 5. So what's given? The x coordinate is given as 5. Find the y coordinate. So the x coordinate is given as 5. That's halfway between 4 and 6. Head up. And you reach this point. And its y coordinate is 6. So y must be 6. So f of 5 is 6 from the graph. Find g4. G of 4. So I head to 4 on the x-axis, that's here. And I got to go to g of 4. So I got to go to the g graph, so which is downwards. And that y coordinate is minus 2. So g of 4 is minus 2. The point is 4 comma minus 2. That was easy. In the graph given below, find f of 6. Okay, things are getting interesting. F of 6. So how do I find f of 6? I first find f of 6 and then that's the input again to f. So let's just find f of 6 first. So f of 6 means the x coordinate is 6, find the y coordinate. When the x coordinate is 6, I go up to the f graph, the y coordinate is 8. So f of 6 is 8. And I need to find f of this. I need to find f of 6, which is f of 8, which means I go to 8 on the x-axis, head to the fx graph, and up here, this point is 12. So f of 8 is 12. It's the top of the graph. So f of 6 is f of 8, which is 12. So I'm using the f graph twice. I put in an input x 6, get an output 8. This becomes my new input. I put it in 8 and I get an output 12. What about f of g of 0? So my first function is g of 0. So I go to 0 on the x-axis, head up to g, that's 2. So g of 0 is 2. And I need to find f of 2. I head up to 2 on the x-axis, and then I got to go to the function fx. But I'm already at the function f because the function f passes through this point and the y coordinate is 0. So f of g of 0 turns out to be 0. G of f of 0. G of f of 0. So I need to find f of 0 first. F of 0, I head to the function f from the point 0. That's going down to this point. So f of 0 is minus 4. The y coordinate is minus 4. And then I need g of minus 4. So I head to minus 4 on the x-axis. Head up to the function g, which is this point, which has a y coordinate of 6. So g of minus 4 is 6. So g of f of 0 is 6. F of g of 0 is not equal to g of f of 0. And there's nothing surprising in that. They're very different functions. So we've learned how to read the composition of functions when we are given the graphs of the functions. We just read each individual graph as and when we have to. Figure out the input, go to the graph, read the output. If they're given the output, go to the graph and figure out the input. The graph of y equal to hx is shown below. Use the graph to find h inverse 0. So recall what the inverse is. Inverse, h inverse. What the inverse does is, it inverts the x and y coordinates. So H has x and y coordinates x comma y. H inverse will have xy coordinates y comma x. The x coordinate of H becomes the y coordinate of H inverse and vice versa. So they're asking for H inverse 0. So what have they given? Well, they've given x coordinate for H inverse. So they've given y coordinate for H. What they're actually asking for is, they're saying that H of some value is 0. Find that value. So we need to find the x coordinate of a point whose y coordinate is 0. So the y coordinate is 0. That means the point is on the x-axis. So I go to the x-axis and this is the point whose y coordinate is 0. What's its x coordinate? 6. So since h of 6 is 0, therefore h inverse 0 is equal to 6. Find h inverse 2. So what have they given me? They've given me the y coordinate is 2 and I need to find the x coordinate. So I need to find h of some value whose y coordinate is 2. In other words, they've given me x comma 2 as the point. Find x. So I go 2 on the y-axis, go to the graph, and here's my point. This is a point with y coordinate 2. What is its x coordinate? 8. So h inverse 2 is equal to 8. Or in other words, h of 8 is equal to 2. Find h inverse minus 8. H inverse minus 8. Again, I got to find an x coordinate whose y coordinate is minus 8. So I head to minus 8 on the y-axis. I find the point. It's here. I find its x coordinate. It's minus 2. So that x is minus 2 for which the y is minus 8. In other words, h inverse minus 8 is minus 2. So it's only notation. Once you know what h inverse means, it becomes a regular problem in H. It just becomes reading the graph of H. So we just looked at an example where they had asked for h inverse of some values, but we only had the graph of H. It would have been much more convenient if we did have the graph of h inverse. So let's relate the graph of a function and the graph of its inverse. It's actually very easy to do because I know if a function hx has points say 2, 3, 4, 7 and minus 1, minus 6. Let's plot this function. 2, 3 is somewhere here, 4, 7 is somewhere here, minus 1, minus 6 is somewhere here. These are the 3 points on the graph. Then h inverse just inverts these points. So h inverse will have the points 3, 2, 7, 4 and minus 6, minus 1. Let me plot h inverse on the same graph. I'll plot it with circles. So it becomes 3, 2. That's here. It becomes 7, 4. That's here. And it becomes minus 6, minus 1, which is here. So you see the original 3 points have their x and y coordinates flipped. And you get the points in h inverse x. So let's see what's happening to one typical point. So let's look at 2, 3. 2, 3 is going to 3, 2 in the inverse. Let me plot 2, 3 properly. 2, 3, let me take. So 2, 3 is here. And it goes to 3, 2. It ends up here. So what's happening to it? Well, the x and y coordinates are being flipped. And geometrically, that means that if I take the line at a 45-degree angle and I reflect the point in that line, I get my point in the inverse. So this point was 2, 3 and this point ends up being 3, 2. So I reflect in the 45-degree line passing through the origin. Why does this work? Because this line actually has equation x equal to y. So I'm reflecting in the line x equal to y. So every coordinate gets flipped. A coordinate of the form a comma b will become b comma a on reflection. And that's what we want for the inverse. We want the x and y coordinates to be flipped. So finding the graph of the inverse is nothing but reflecting every point on the graph through the line y equal to x. Or in other words, flipping the x and y coordinates of every point. The interesting question is, suppose I have a linear function, that is a line, a straight line, and I find the inverse of the function, will it stay a straight line? Well, it will, because if I take any straight line, say I take this straight line, how do I find the inverse? I have to flip this in the line y equal to x. So first draw the line y equal to x. And I have to reflect it in this line. Well, this point is on the line, so it won't get reflected. It will stay its own image. How about this point? This point, I draw perpendicular to the line, and I go the same distance here. How about this point? I draw perpendicular to the line, I go the same distance on the opposite side. How about this line? I draw perpendicular to the line, and I go the same distance this side. So, my original line will become this new line. So, this line, if I call it f of x, then this line is f inverse x. This is the graph of y equal to fx. This is the graph of y equal to f inverse x. The line is reflected in the line y equal to x. And every line stays a straight line. That's how you obtain the inverse of a linear function. How about the inverse of a quadratic function? So what's a quadratic function? It's a function which has y equal to x square plus something, maybe plus 3, or y equal to x minus 4 square plus 7 or whatever. So it looks like a parabola. Quadratic functions look like parabolas. This is what a typical quadratic function looks like. Okay, I'm going to take the simplest quadratic function. I'm going to take y equal to x square. So this is my quadratic function, y equal to x square. And I'm going to flip it as usual in the line y equal to x. So what happens is I get this curve. I get a parabola which now opens to the right. The original parabola was opening upwards. So this is the inverse function. So I've flipped x and y. So this is the function x equal to y square. So you can see there's a problem with this function. It's not really a problem. There's a characteristic of this function that for each x value, now I have two y values. So if I were to write it as a function in y square equal to x, if I were to take square roots, I'd get y is equal to plus or minus root x. As you can see, for each x value, I'm getting two y values. I'm getting y equal to plus root x and I'm getting y equal to minus root x. So that's what explains for each x value, I'm getting a positive value and I'm getting a negative value. If this was 4, this point would be 4 comma 2 and this point would be 4 comma minus 2. Root 4 is 2, so I'd get 4 comma 2 and 4 comma minus 2. So the inverse of a quadratic function is giving me two functions. It's giving me this function and it's giving me this function. Why is that? Because for a given x, I can't have two y values. That isn't allowed in a function. Remember that for any x, there should be exactly one y value. Otherwise, it isn't a function. So y equal to plus minus root x is not a function. But I can make two functions out of it. I call the upper branch y equal to root x and the lower branch y equal to minus root x. So I get two functions out of this one relation, as it were. So the inverse of y equal to x square is not a function because it's x equal to y square. That is y square equal to x, and this isn't a function. This is two functions, plus root x and minus root x. So you have to divide the inverse into two separate functions. Graph transformations. Here's another thing that students find very tricky. Actually, it's very simple to understand. It basically boils down to the notion of understanding how you plot a graph. You give it an x value and you get a y value, and then you plot the graph. You don't first figure out what happens to the graph. You actually take x values, figure out the y values, and that leads you to what the graph looks like. So let's look at a simple example. Suppose I have a graph like this. And I say, I want to move this graph up and down, left and right. That's what I mean by a graph transformation. I'm moving the graph on the coordinate plane. So suppose I move it to this point. So we know that this is the origin 0, 0, and the entire graph moves to the point 3 minus 2. Then how do we describe this motion? Well, we know it's moved 3 to the right and 2 down. That's what's happened to the graph. So geometrically, it's very easy to see. It's just a translation. A translation means the entire graph moves in the plane. So if one point moves 3 right and 2 down, then every point moves 3 right and 2 down. The graph doesn't change shape at all. The entire graph just moves. So let's see, given an equation, how do I relate the equation to a translation? Use the graph of fx equal to x square shown below to draw the graph of fx plus 3. That is of x square plus 3. So this is my graph of x square, and I need to draw the graph of x square plus 3. So let's understand how we plotted this graph. Well, we took x values and we found out x square values. So if I took 0, I got 0. If I took 1, I got 1. 2, I got 4. Minus 2, I got 4. 3, I got 9. Minus 3, I got 9. And after calculating all these values, I plotted them and then connected all those points to get the entire graph. Now I have to plot the graph of x square plus 3. So I'll take the same x values and I'll see what this new graph is. So when I take 0, x square plus 3 is 3. When I take 1, it's 4. When I take 2, it's 7. When I take minus 2, it's 7. When I take 3, it's 12. When I take minus 3, it's 12. So if you compare to the original graph, each value has been hiked up by 3. Each y value. For the same x value, the difference in the y values is 3. So if the original graph was 2, 4, the new graph has the point 2, 7. For the same x value, the y value has changed by plus 3. That's what the plus 3 in the function is. So what will be the new graph? Well, if the old graph was this, for each x value, the y value is going up 3. For each x value, the y value is going up 3. For each old x value, the y value is going up 3. So the entire graph has moved up 3 units. That's all that's happened. The entire graph has been translated up 3 units. Every y coordinate is 3 units more than the earlier y coordinate for the same x coordinate. It's moved up 3 units. Now it's easy to understand what's happening at the function level. The original function was x square, y was x square, and the new y is x square plus 3. So we can see that adding 3 to the y value just hikes up every y value by 3, obviously. What happens to the graph? The graph moves up 3 units. Same thing. The same graph x square. Now the new function is f of x plus 2. 2 is being added to each x coordinate and then the function is being calculated. So let's look at our original graph. X square, 0, 0, 1, 1, minus 1, 1, 2, 4, minus 2, 4, 3, 9, minus 3, 9. This is how the graph of x square was plotted. You have to keep in mind the parent graph, the original graph. How was it plotted? If you don't know how that was plotted, if you don't have control over that, you're not going to understand what happens to later graphs. Now they want f of x plus 2. So what's f of x plus 2? Well, f of x plus 2 is x plus 2 squared. Remember, put in whatever is here as x. So it's x plus 2 squared. They want x plus 2 squared. That's my new y. So when x is 0, I get 4. When x is 1, I get 9. When x is minus 1, I get minus 1 plus 2, that's 1. 1 squared is 1. When x is 2, I get 2 plus 2 squared, that's 16. When x is minus 2, I get minus 2 plus 2 squared, that's 0 squared, that's 0. When x is 3, I get 3 plus 2 squared, that's 25. When x is minus 3, I get minus 3 plus 2 squared, that's minus 1 squared, that's 1. So these values have all gone haywire. There doesn't seem to be any connection between the original y values and the new y values. Well, because there isn't. There is no connection between the original y values and the new values. The connection here is with the original x values and the new x values. What we've done is we've added 2 to x and then we've calculated y. Well, anyway, let's plot these points. What are the points? First point is 0, 4, 1, 9, minus 1, 1, 2, 16, minus 2, 0, 3, 25, and minus 3, 1. So these are the points I have to plot. So let me make some space for these points. I'll erase this. I don't need it. Here's my original graph, y equal to x squared. And now, were I to plot these points, I would get this graph. If you were to plot it carefully. And this is minus 2. As you can see, minus 2 gives me 0. And then minus 1 and minus 3 both give me 1. So minus 3 gives me 1 and minus 1 gives me 1. And then 0 gives me 4. And you would see that minus 4 would also give 4 because minus 4 plus 2 is 2 square, which is 4. So minus 4 also gives 4. So 0 would give 4 and minus 4 would also give 4 and so on. So something very interesting is happening. The graph seems to have moved left and it's still a nice parabola. So moved left 2 units. So when I add 2 to x within the function, if I want to plot the function f of x plus 2, that means x plus 2 the whole square, the graph has moved left 2 units. Totally counterintuitive, but let's understand it. So what happens is that in the original graph, I took a value of x and I got a corresponding value of y. So say I took a value of x as 2 and I got a value of y as 4. That's in my original graph, y equal to x squared. Now, I still want the value of y to be 4. What value of x will I have to take in the new graph? So, I want the value of y to be 4. So, I want x plus 2 square to be 4. What value of x will give me that? Well, a value of x 2 less. If originally a value of x equal to 2 worked, now a value of 0 will work because I'm adding 2 to it. So you see, I need to take an x value which is 2 less to achieve the same y value as before. Because this new x value is being increased by 2. I'm adding 2 to it. So I need 2 less to start with to achieve the same y value. Which is why to get the same height in the graph, I need to go left 2 units. When I go left 2 units, I achieve the same y value. Use the graph of fx equal to mod x to draw the graph of gx equal to mod of x minus 2. So what have I done? Fx is being transformed to f of x minus 2. Well, everyone knows the graph of fx. This is the graph of fx. Why is that so? Let's take some values. X and mod x. So x is minus 2, 2, minus 1, plus 1, 0, 0, 1, 1, 2, 2. So all negative values are made positive, all positive values stay the same. So I've plotted 1, 1, 2, 2, 3, 3, 4, 4, minus 1, 1, minus 2, 2, minus 3, 3, minus 4, 4, and so on. They're just two straight lines. Here y is equal to x and here y is equal to minus x. Because when x is negative, I got to negate that value to get y. So I'm negating x on the left side. On the right side of the origin, y just stays x. So y equal to mod x is actually y equal to x and y equal to minus x when x is greater than or equal to 0 and when x is less than 0. We've seen this definition before, y equal to mod x. Well, anyway, here x and mod x, we've plotted the graph. Let's find out what's the graph of mod of x minus 2. So let's find the y coordinates for this new function, mod of x minus 2. So when x is minus 2, I get 4. When x is minus 1, I get 3. When x is 0, I get 2. When x is 1, I get 1. When x is 2, I get 0. Let's take a few more values. 3, 4, 5. I'll get 1, 2, 3. So what's happening? Well, 2 is ending up at 0 and then things are increasing both sides. So the new graph would be at 2 it's 0 and then we have the same graph. So this is the graph of mod of x minus 2. Let me draw them both together. So here's graph of y equal to mod x. And here's the graph of y equal to mod of x minus 2. So as I've subtracted 2 from each x value, the graph seems to have moved 2 to the right. And that's exactly what's happened. 2 to the right. Let's try to understand it. So let's look at this point. To obtain this y value of 0, I had to take x equal to 0. To obtain the same y value in the new graph, what will I have to take? X. To obtain the y value of 0, I need to take x 2 more than originally because I'm going to subtract 2 from it before I calculate the y value. So if I take x equal to 2, mod of x minus 2 will become 0. Let's look at this value. Say this is minus 3, 3. Suppose this point is minus 3, 3 in the original graph. So the original graph had a point minus 3, 3. To achieve the same y value in the graph x minus 2, what do I have to take x as? So I want the y value to be 3. I'll have to take x as minus 1. So minus 1 minus 2 mod is 3. So I'll have to take x as minus 1. So I've added 2 to the x value to achieve the same y value. So that's what's happening. When I subtract 2 from x within the function to achieve the same y values, I need to hike up x by 2. So the graph moves right by 2. So the graph of x square has been translated as shown. Write the equation of the translated function. Okay. So the original graph was pivoted at 0. This was the original graph. And it's moved to this graph as shown. So we know the translation because we know where the vertex of each parabola is. The original graph had vertex at 0, 0. And now it's moved to this point, which is 3 minus 2. So what's the translation? It's gone 3 to the right and 2 down. And they want the equation. So I know to achieve 2 down is easy. I just subtract 2 from every y coordinate. So the new graph would be x square minus 2. If the new graph was x square minus 2, I know the vertex would go 2 down. The entire graph would go 2 down. That means the graph would end up here. It would just go 2 down. This would be the graph of x square minus 2. Well, having moved it 2 down, I now need to move it 3 to the right. To move it 3 to the right, each x coordinate has to be played with. So if the original x coordinate was 0, to achieve the same y coordinate, I need to subtract 3. X minus 3 square minus 2.
Because now when I plug in 3, I will get 0. So when originally I plugged in 0, I got 0. Here I have to plug in 3 to get 0. Because I'm subtracting 3. So x minus 3 square minus 2 is my answer. So here we have the most abstract form of a translation. So fx becomes f of x minus h plus k. What are the transformations? Well, the plus k to the entire function tells me that it's moving up k. That means if fx just became fx plus k, I'm just adding k to each y value, so it moves up k. Now this fx plus k has become f of x minus h plus k. Now I'm subtracting h from each x value. So I better hike up each x value by h so that I achieve the same result. Because I'm going to then subtract h from each x value. So if an original x value was 3, I need to add h to that 3. So I have to move right h units. The graph will move right h units to achieve the f of x minus h. So the entire graph has moved right h units and up k units. That's what's happened. Okay, I think that's enough of the basics of the graphs of functions. I'll leave you with a very mathy joke.